derive this expression here, that we decompose this in terms of the L components, the angular momentum, and we have minus TL divided by K. I think that's a factor of pi also. Here, pi, and times the Legendre polynomial cos theta, like this. And this thing here we call FL, this function of K. This should be E here, not L, should be E, like that. And DE is the matrix element. It's also a function of L, of course. It's just the matrix element in the angular momentum state. Like this, yes. So this is the main result we got last time. So then we analyze the asymptotic solution of the scattering state, and that of course can also be expanded in terms of its angular momentum component, like we have here. And the interesting thing about this expression is that there are two components. There is the outgoing spherical wave, so that's outgoing, and there is the incoming spherical wave. And the incoming spherical wave is not affected by the scattering potential, and only the outgoing spherical wave is affected by the scattering potential. So we have this scattering amplitude, which we call SL, so that's a function of K. So we can think of the incoming spherical wave here as a background solution, so that is part of the homogeneous solution to the Schrödinger equation. Since we are looking at the outgoing solution, then that incoming part is not affected. So only the outgoing part is affected. We are looking at the plus I eta solution. And then we define the phase shifts. So first of all, that we are looking at elastic scattering. So this means that we conserve number of particles. The number of incoming particles is equal to number of outgoing particles. So this implies that the magnitude of the scattering amplitude M is SL must be equal to 1, because there is no attenuation, there is no absorption of particles by the scattering potential. So it has a magnitude 1, and it's a complex number, so we can write it as an exponential of some phase. So this is what we have, I think, last time. So we define that phase, delta L, and there's a factor of 2. That's just a definition, and we'll see why we have that. Okay, so I think that, yes, yeah, I think we also did this part here. So this the L component of the scattering amplitude can be written in several ways, but these are just rewriting things. So it depends on the problem. We sometimes wants to use this expression and sometimes this one, and yeah, or maybe even the first one. So these are all the same thing. Well, so now in terms of the phase shifts, the scattering amplitude is a function of the angle theta. So the angle theta is, once again, it's the angle between the K prime and K. So the scattering amplitude depends only on that angle because of the spherical symmetry. It can be written in terms of this phase factor. So it is quite nice, I think, scattering theory, because all the information about the scattering properties can be obtained from the phase shifts. So the only thing we need to know is the phase shifts. So the phase shifts then plays a key role in the scattering theory. So everything is condensed into this quantity, the phase shifts. If we know the phase shifts, then we know the scattering wave functions asymptotically. So that's all we need to know, the phase shifts. Now, this is actually a nice example to show that the optical theorem is fulfilled for this scattering amplitude. Well, it should be, because it's an exact expression. So let's show that. So we have it also in the note here. So we want to show that the optical theorem. It says that the imaginary part of the forward scattering amplitude, so that's theta equal to 0, is equal to 4 pi upon k, I think, times the total cross-section, scattering cross-section. Well, we just use this expression. We know f theta. So let's first calculate the total scattering amplitude. So that is then integrate over the solid angle of d sigma d phi and d sigma d omega, I mean. And this is just the square of the scattering amplitude. That's we have defined, we have found that in the very beginning. So now we use the expressions for the f theta. So all we have to do is just take the square of that. So we have to sum over L and L prime. So there is this 2L plus 1 and L prime plus 1. And then we have the phase into the delta L. And we have another one. So that's minus because we are taking the complex conjugate. And then we have the sign, the 2 sine L sine delta L prime, like this. And then we write this integral. So this is in the spherical coordinates. So we have integral over the azimuthal angle from 0 to 2 pi and from minus 1 to 1 of dy, where y as usual is cosθ. Yes, so then we have the integral over phi is just 2 pi because we have no dependence on the azimuthal angle. So we just have an integral over the y variable. So that's between two Legendre polynomial, PL and PL prime. Okay, so now we make use of the orthogonality of the Legendre polynomial. So that is equal to 2 delta LL prime divided by 2L plus 1. So then we get, what do we get here? Sorry, there's a 2 pi, I have already included the 2 pi here, so I should move that. So that should be just one, I think. So then we get 4 pi upon k squared sum over L plus 1. So sine squared delta L. That's our total scattering cross section. So we want to check if this is equal to the imaginary part of F. Well, we just take the imaginary part of F for theta equal to 0. So that is equal to 1 upon K sum over L plus 1. Now we take the imaginary part of di delta L sine delta L and PL theta equal to 1, so that corresponds to 1 because cos 0 is equal to 1, and that is just 1, so this is just equal to 1, and this is equal to sine delta L. So you see it's the same, yes, so it fulfills the, apart from this factor of 4 pi upon k, so that is equal to, yeah, so that is equal to then 4 pi upon k times, so is it the other way around? Seems that I have, let me check, pi k total. Optical theorem, I forgot. Ah, it's okay. Okay, so it is, that's fine. So that's equal to k, so I made a mistake here, it should be opposite, yes. So it should be k divided by 4 pi. So that then fit times sigma total. So that's nice, as it should be, because it's an exact expression. So that fulfills the optical theorem. But we can take another example, which does not fulfill the optical theorem. So this is the Born approximation, just to illustrate that approximate theory does not necessarily fulfill the optical theorem. So we have, in general, the scattering amplitude is given by some constant. We need not worry about K prime, and then we have potential, and then we have the outgoing solution. So that is written in terms of the T matrix, or the T operator. This way, yeah. And so this is not Born approximation, this is exact. And the T operator, or the T matrix, if we expand it in terms of the scattering potential, then we have the perturbation series. Like that, and higher order. So there's first order, second order, and third order, and so on. So if we look at the first order Born approximation, so this is first order. So usually when we say Born approximation, it is meant to be first order, but I think it is better to say explicitly first order Born approximation, because sometimes we go to higher order. So in first order, then if you look at the forward scattering, so theta equal to 0, that would means that k prime is equal to k, because we are looking at the elastic scattering and the forward, so there is no angle in between k and k prime. So this is obviously then a real quantity, because it would be like k prime, just k, be k like that. So this is real. It's a real quantity, because it's expectation value of Hermitian operator. Yes, V is Hermitian. So then obviously the optical theorem is not fulfilled here, because the imaginary part is 0, whereas the total scattering amplitude, the total cross section is not 0. Yeah? It's the square of this integrated over the solid angle. So this means that imaginary part of is not equal to, what was it, k upon 4 pi total, obviously. But if we go to higher order, then we see that we will start getting some imaginary part, because we have this I eta. So we will have the imaginary part then will be like V, then delta E minus E0. So I neglect all the constants. I just want to show you the main matrix elements. So we'll have some imaginary part coming from this second order term. So we can see that as we include higher order perturbation terms in T, then the optical theorem is eventually fulfilled, because it becomes an exact solution. Now, if we want to construct an approximate theory, it could be a good idea to impose the optical theorem. So the approximate theory fulfills the optical theorem. So even though it is approximate, it's not exact, one could construct an approximation such that it fulfills the optical theorem, or at least that it gives a result which is as close as possible to the optical theorem. That's one use of this optical theorem. Okay, so that's just an example. So the key question now is that how we determine the phase shift, how to determine the phase shifts and the bells, because these are the key quantities in scattering theory. So if we look at the problem, so we have a spherically symmetric potential V, and that's why we took the origin to be the center of the potential. So outside the potential, then the solution should be just the linear combinations of free particle solution. So outside, so if we call this capital R, I call it capital R here. So outside, so this is outside the scattering region. Then the solution for each L component is just a linear combinations of the free particle solution. So the Schrödinger equation is second order. So there will be two independent solutions. So one is called the regular solution. and that is just the spherical Bessel's functions, KR. And the other solution is the irregular one. So call it BL, and you can use NL, KR, like this. So this is regular, and this is irregular. So by irregular, we mean that it diverges at the origin. So the solution is not allowed at the origin, diverges at or equal to 0. So it's important to note that it's divergent. So if you have a situation, let's say you have a potential like this, let's say like a donut, where there is nothing in the inside here, so the potential is only confined here, then the solution inside here can only be a Bessel's function. We cannot have the irregular solution because it diverges. Or if we have just like a square well, or not the square well, but just a well, it's constant potential, like that. So let's say it's constant inside some radius. Then also the irregular solution is not allowed. We only have the Bessel's function, spherical Bessel's function inside this, if this is a constant. So that's important to keep in mind. So we want now to determine these coefficients, EL and BL, by using the boundary conditions that asymptotically it should match our solution, asymptotic solution that we worked out before. So we want to use the asymptotic boundary condition. So we look at the solution with very large R. And to do this, it is convenient to work with the Hankel's functions. We don't have to do this, but it's easier because we know the asymptotic solution in terms of exponential. So it is easier to match it to the asymptotic solution that we already worked out. So there are two Hankel functions, the first and the second kind. So these are just equivalent to the Bessel and this function, irregular function, and L. So it's just a linear combination of these two. So these are equivalent to JL and NL. Yes, yeah. So this is math. So the first Hankel's function. So it is asymptotically. So this is asymptotic. So large. That's R goes to infinity here. It goes like plane wave, spherical plane. It's not a plane wave, but spherical wave on I, K, R, like this. So this would be the outgoing. And the second Hankel function goes like an ingoing spherical wave. So this is ingoing or incoming. Okay, so this the asymptotic expansion of the Hankel functions. So the solutions Then if we write it in terms of the Hankel function, then we will have different coefficient. Of course, call it CL1 and C2L for the second Hankel functions. Like this. So now we write the solution, the scattering solution. So there is a factor of L to the 3 halves, so that's square root of the volume. So L R and then P cos theta. And this is for R here and R. So we're looking at the free particle solutions. So this is a general expansion because we have a spherically symmetric potential. We can always write a solution like this. Yes. So this function L or here will go over to the spherical Bessel's functions. Yes. When the scattering potential is 0. So the irregular part disappears because it's not allowed to include that because it diverges at the origin. So we now want to determine the coefficients. So we want to determine this and this one. So we want to determine this. And to do this, as we mentioned before, we match or we compare this expression here to the asymptotic solution. So we look at the asymptotic solution of psi r. So that goes over 1 upon 3 half and cos theta. And then we have and then we have this incoming solution. So if we compare these two expressions here using the asymptotic form of AL that we have written in terms of the Hankel's functions, then we see that AL is then equal to 1/2 e to the 2 delta L times the Hankel function. So that is equal to So we use the expression for the first Hankel function. Like so. Then we can identify the coefficients. Yes. So the first one is then equal to 1/2 I to I delta L, and the second one is equal to 1/2. So actually, I should have written this first before going here. Yes. So that comes from comparing this expression and this expression here. Okay, so then the final result, which is what we are after, is given by this. Goes delta L and then R minus sine delta L and times the irregular solution. So comes from this one here. So I just combine the spherical Bessel function terms. So that gives me the cosine, and that one gives me a sine. So this is the key result here. So this is the solution for R bigger than R. So for each L component, the solution can be written in terms of the phase shifts. This phase shifts delta L. So that's a nice thing about the spherical potential. The angular momentum commutes with the Hamiltonian, so then the solution can be treated for each angular momentum can be treated separately, independent of each other. This is the solution outside the potential, and we also have solution inside the potential. And in order to determine the phase shifts, so the phase shifts is or are determined by matching the solution inside and outside. So we have the wave function itself and also the derivatives. So we want to have psi and the derivatives at the boundary equal to R. So we want to match the solutions inside and outside at the boundary. So they have to be continuous. Now, in order to determine the phase shifts, it is actually only necessary to calculate the ratio of psi prime of the solutions, the ratio of the derivatives and the solution itself. So there is an logarithmic derivatives. Yes. So this would be the logarithmic of psi prime, like this. So that's the only thing we need to know in order to determine the phase shifts. We don't need to know the absolute value of the wave function. We only need to know the logarithmic derivatives. So that is an important point. We need just the logarithmic derivative. So the solution inside, of course, depends on the potential, depends on the shape of the potential and the strength of the potential. The only thing we know is it's spherically symmetric. We have to solve the solution inside potential. And that usually we have to do it numerically because we don't know what the potential is. If it is a simple potential, it's like just a constant, then we know it's just a free particle solution with a modified energy. But in general, we don't know. So it can be some Coulomb potential or some other potential. So the solution has to be obtained numerically. So let's say that the solution inside is called A, L inside here. And then the logarithmic derivative for the solution, I shouldn't call it, maybe that's the outside. So let me call it RL inside. So the logarithmic derivatives from inside is, so from inside is given by the RLDR calculated at R to R divided by RL. Right? So by convention, we include the radius here, so to make this dimensionless. We have a dimensionless quantity, but this is just a convention. So define it like this to be our definition of logarithmic derivatives. So then all we have to do is to match this to the logarithmic derivative of the solution outside. Like this. So this is from outside. So that's the free particle solution. And that gives us then the expression for the phase shifts. So if we calculate this logarithmic derivatives, we will find that it is equal to Kr, and then we have cosine delta L prime Kr minus sine divided by EL. So that is given by this. So these are just the numerator is just the derivative of AL, and the numerator denominator is just AL times R here. So we have this equation equal to beta L, and this is obtained numerically usually because we don't know what the potential is. So that's the logarithmic derivative from the inside solution. So this then gives us solution for the phase shifts. So we divide everything by cos, and we get a tangent, and that is given by, it's just a little algebra, and you can check this. By K KR. like that. So that's the explicit expression for the phase shifts. So the information about scattering properties, this is of the scattering potential, is contained in this phase shift here. So it contains information about the scattering potential. So the scattering potential comes in beta. So the logarithmic derivatives of the solution from inside is given by beta L, and that contains the information about the scattering potential. So it's a very interesting result, because the only thing we need to know is the logarithmic derivatives of the solution. We know nothing about the detail of the solution inside. The only thing we need to know is logarithmic derivatives, and that is enough to determine the phase shifts and therefore the solutions of the scattering state. So it's a bit surprising that we do not need to know the details of the solution inside. We just need to know how it behaves at the boundary. So the solutions in terms of the logarithmic derivatives. So this implies that there could be then many potentials that gives us the same logarithmic derivatives. So many potentials, spherically symmetric potentials in this case, we understand. So many potentials that have the same logarithmic derivatives. Yeah. At least for a given angular momentum component. Yes. So it may not be possible to have the same logarithmic derivatives for all the angular momentum components, but at least for one or for a few, it's possible to have this. So these properties can actually be made use by what is called a pseudopotential. So this leads to the ideal pseudopotential. So what one does is that one replaces the original potential, which can be very strong, by another potential, which is much weaker, but nevertheless has the same logarithmic derivatives. So if we are only interested in the scattering properties of the potential, it is then possible to use this pseudopotential. So you use a weaker potential, which can be handled more conveniently numerically if you have a weaker potential than a stronger potential. This is one use of these properties. So that is a bit of just an aside. A weaker potential. Okay, so this could be a good point to have a break. And then in the second half, we will consider a couple of examples to illustrate how we determine the phase shifts. So, are there any questions up to here? So there is a question about exams here. See, um, okay, I can upload some previous exams if you like. So, okay, let me take a note. So I would say that typically I try to avoid lengthy calculations. So I just want to, um, yeah, examine the understanding, yes, rather than doing tedious calculations. But sometimes it is unavoidable to do some calculations. Then in that case, I will try to minimize the algebra. So, for example, if you have a lot of constants in the equations, you can just define it instead of rewriting the same thing again and again. So that saves time. And I'm usually not worried too much about sign or constants, things like this. It's most important things that one understands. Yeah. Okay. Are there any more questions? And also, I suggest that you do a little practice about these practical things of having a camera behind you or beside you. I'm really sorry about this, but so far, I think it's the best solution. It's a bit stressful to have a camera behind. Okay, if there are no more questions, then we come back at the quarter past as usual. this quote pause. Let's continue. So let's summarize what we have done so far. So the key quantity here is this logarithmic derivative of the solutions at the boundary, so that r equal to capital R. So what we do is we match the logarithmic derivatives at the boundary. So we say that the logarithmic derivative from the inside solution is given by beta L, which has to be calculated, and that depends on the potential. And we have the logarithmic derivative from outside, so that's from the free particle solution. And that we know analytically. And from this matching, we can then determine the phase shifts, delta L. And if we know the phase shifts, then we know the scattering amplitude, which is the main quantity we want to know in scattering theory, because that tells us how the scattering wave functions looks like. Okay, so this is actually an exact way of determining the scattering wave function. If we use perturbation theory, like the Born approximation, then we do not need to go through all this. All we have to do is just calculate the matrix elements of the scattering potential in the plane wave. Yes, and the potential is actually not even have to be doesn't even have to be spherically symmetric if we use Born approximation. So the Born approximation is a general perturbation theory, so it does not require that the potential is spherically symmetric. So you can have an arbitrary potential. So that's a nice thing about the Born approximation. But of course it has limitations, as we have seen, that it does not fulfill the optical theorem, and then also there are other problems when the potential becomes too strong. It's not valid anymore. But otherwise, it's a general approximation that can be used for any potential. And here, when we solve the problem exactly, we need to know the logarithmic derivatives which match the boundary. Okay, so now let's consider some example. So we start with maybe a simplest case. We have a hard sphere. So we imagine we have a potential. So this is the radial distance. This is the origin here, and we have potential. So that's capital R, and this is infinite here, going up here. So that's what we mean by hard sphere. So if we look at it from the top, we get the projection, that would be just a sphere like this. Yes. So no particle can penetrate the region inside the potential, the hard sphere. So we want to write it more properly, so that is equal to infinity for r less than r is equal to 0 for r bigger than r. So then we have the solution outside, which is goes L K R minus sine delta L or like this times this phase like that. So that's the solution outside. we just worked out. Because we have a hard sphere, then the solution at R must be just 0, because there is no possibility of penetrating inside. So if we calculate the solution at the boundary, we look at the solution at the boundary, so then this has to be equal to 0. So that would imply that the tangent, so I jump a little bit here, the whole thing becomes 0, and I can divide by cosine. I get tangent is just the ratio between the spherical Bessel's function and the irregular solution. So then we get the solution right away. And that's an easy case. So very often we are interested in low energy scattering. By low energy, we mean that the wavelength is much bigger than the size of the potential, the radius of the potential in this case. So that implies that if we use k instead, so k is equal, momentum is 2 pi upon lambda. So that would then imply that k times r is much less than 1. So that's the criterion for low energy scattering. In that case, we can make an expansion in the powers of kr. So then this tangent of delta L, of the phase shifts, becomes, so let me write this. So this is the expansion of spherical Bessel's functions. Double factorial divided by the irregular solution, which is, so this is math, just have to accept it here, L plus 1, so that's the small kr expansion of the spherical Bessel functions and the irregular solutions. So this is the double factorial, and you know that the double factorial means n times n minus 2 instead of minus 1, so and n factorial is equal to 1 for n equal to 0 or minus 1. Yes, that's a convention. So if we take the L equal to 0, so that's usually is the most important component, the low L. We then get tangent delta 0 is equal to, so actually we know the analytic solution for the Bessel's function is just given by sine kr divided by kr, and the regular solution is cosine with a minus sign divided by kr. So that gives us then just minus tangent kr. So then delta 0 is equal to minus kr. So if we look at the solution, for the L equal to 0, then it becomes, so this is proportional to the 0 plus cosine QR or sine delta 0. So then it becomes 1 upon QR sine QR plus delta 0. So delta 0 is equal to minus QR. So then this becomes 1 upon QR sine K R minus R. So you see from this example why this is called phase shifts. Yes, because it shifts the solution by this amount, delta. So we look at the solution, we have something like this. So this is our scattering potential R. So without the scattering potential, then the solution will be just the Bessel's function, spherical Bessel's function. So that will be just sine divided by R. So this is no potential. So that would be just the sine KR divided by KR. With the potential, the solution is just shifted. So you will start here. It's exactly the same solution, but shifted by this amount here. So that is R, of course. So that is given by minus delta 0 divided by K. So that gives some illustration about the meaning of this phase shift. And delta shifts the potential. And that basically what it does. So each angular momentum component of the solution is shifted depending on the value of L. So it's shifted by this amount here. So that, yes, there's any question? Yes.
Is this really a solution? Because the fact that the potential is infinite at radius r and before, it makes that all the energies should not enter the sphere. So when we make the low energy assumption, we kind of really restrict all the solutions of the problem. So it might not be a solution, this one.
Okay, so this one is actually for the L equal to 0. This is actually the exact solution. Yes, it's not. There is no approximation here because the J
so because we look at L equals to 0 means the energy must be below 2.
Yeah.
Ground state. Okay.
Yeah. Yeah. Right. So, but in any case, even if you look at the higher L, it will still be true. There should not be any weight inside because the potential is infinite. Yes. So that's how the solution looks like. And so basically in this case, it just shifts the potential. And And we'll consider a more realistic potential, which is have a finite strength. But let's look at the differential cross-section. So this is given by the square of the scattering amplitude. So that is then equal to k squared. So that comes from the general formula of the scattering amplitude is FL. Yes. If you look at the expansion of F in terms of sum over L, then you look at the L equal to 0 component, then you get this result here. It's just the sine squared of delta 0 divided by k squared. So that comes from the general formula. So when the energy is low, so then that's approximately equal to squared, so that delta 0 is small, and that is equal to r squared then, because delta 0 is the minus kr. So the total cross-section, which is integral over the solid angle, in this case, this will be just r squared, so then this becomes 4 pi r squared. So this is a little bit surprising because you think about the problem. We have scattering potential. This is a hard sphere. So classically, you would think that this total scattering cross-section should be equal to pi r squared. It's the area of the sphere if you look at the cross-section. But it is 4 pi r squared instead. So that is kind of characteristic of the wave properties of the particle. Because when the wavelength of the particle is comparable to the scattering potential, then we will see some quantum mechanical effects that gives rise to this interference effect that kind of enhances total scattering cross-section. So that's one example. So now we also want to consider more realistic case. So before we do that, let's look at the Schrödinger equation. So the Schrödinger equation, the radial Schrödinger equation, will consist of the scattering potential, yeah. But in addition, we will also have kind of a centrifugal potential, repulsive centrifugal potential that goes like 1 upon r squared. So here we can then also understand why the L equal to 0 is most important. Because for L equal to 0, the centrifugal potential is 0. So then there is no repulsive potential. But for finite L, then we will have this repulsive potential, which is very strong because it goes like 1 upon r squared. So if we get close to the center, it will be stronger than than the scattering potential. Well, unless the scattering potential it goes like 1 upon r cubed or something. But normally we have a Coulombic potential that goes like 1 upon r, or even weaker potential. So the centrifugal part is usually very strong, and therefore the L bigger than 0 become less important. So the higher L, the higher the angular momentum, the less important it is, because most of the components will be repelled by the potential. They cannot penetrate inside the scattering potential. So you can also show by making expansions that this phase shifts will go like k upon 2l plus 1. So we didn't derive it here, but it is not difficult to do. It's just a matter of expanding the Bessel's functions and the irregular solution. Yep. You'll find that it goes like this, k to the 2l plus 1. So that explains that as a k is small, so if you have a low energy scattering, k will be small, so then the L equal to 0 is the most important. So 0 is most important. For low energy scattering. So in most cases, we can neglect the higher L component, just keep the L equal to 0. Because if the energy is high, then it's a different matter. We have to include also the high L components. So let's consider now the second example. So this would be barrier constant barrier. So we have potential like this, for example. So this is 0. This is, so we have a finite height. So, 0 or less than or, and 0 outside. Like that. So let's just look at the L equal to 0 component, because that's the most important. And also that's a simple solution for the Bessel's functions. So we know that this is equal to sine kr divided by kr, and it is minus this one divided by kr. So we know the analytic form of this. So then the solution for the L equal to 0 component so I'm just writing down the general solution here. It should be sine kr. So now if I use this expression here and this expression here, then we see that we can rewrite this as sine kr plus delta 0 divided by kr So this is a solution for R bigger than capital R. So that's the outside solution. So again, we see this thing here, the phase. It shifts the component, the wave functions, the partial wave, by that amount, delta 0. So that's why it's called the phase shifts. It simply shifts the partial waves. So that's a nice, simple physical interpretation. So that's the solution outside. And we have to figure out also the solution inside, because we want to match the solution, the two solutions at the boundary. Here the boundary is at capital R. So the solution inside is also a free particle solution, but the energy is now modified by this V0. Yes. And we have to be careful now, because for the solution inside, we cannot have the irregular solution. So solution R less than or no irregular solution. So that's important, because it's divergence, this solution. So we only have the Bessel, spherical Bessel's function. So then the solution inside will be equal to call it C here. Why do I call it C? Yeah, I think these are just some phase factor, some constant. Prime R divided by R. Or you can include K prime if you like. Yes, doesn't matter. That's a constant. And K prime is defined in such a way that kinetic energy here is equal to E minus V0. Because we are now inside this region here, so that is offset by V0. So the K prime is different from the K. So it can happen that E minus V0 becomes negative. So in that case, then the K prime becomes complex, against imaginary, becomes like what do I call it here? I think kappa. So it will be, replace it with a kappa like that. Become imaginary. And instead of sine, we will have hyperbolic sine. Yes. So that's just a remark. Okay, so let's look at the case when it is not, when this is positive. So we look at the boundary and we calculate the logarithmic derivative. So this is the key step. Logarithmic derivatives at R, capital R. So we calculate the beta 0. So that's the solution from the solution inside. So that's given by this at R, and dA0 R calculated at R. So if we just plug in A0, so that is C times sine K prime R divided by R, then we get K prime times R here. skip some algebra. It's quite simple, I think. Cotangent K prime R minus 1. We calculate this logarithmic derivative. So that we can calculate. We know the logarithmic derivatives from inside. Then we can calculate the phase shifts. From our general formula. So that is given by K on J0 prime KR minus beta 0 J0 KR divided by KR and 0 prime. Yeah, like this. Now we can make a small KR expansion. So KR much less than 1. Then we find delta 0. I think it's a lot of details here, so I'm not going to do all these expansions. I just write down the final result. It is quite clear what to do. So you just make an expansion of the sine and the cosine, basically, and just keep the main terms in the expansion. And if you do that, you get this result here. Like this. So we can also write it in terms of cotangent. So that become K cotangent delta 0. This becomes minus plus beta 0 divided by or beta 0. So this is for the low energy expansion. And we can define this quantity to be equal to minus 1 upon A. It's just a definition here. So this is a definition. So A is defined like this. And this A is usually called, it's called the scattering length. And we can see why. So if we calculate now the total scattering section, so that is integral over solid angles. Then you get 4 pi from the solid angle, and we have tangent delta 0 minus ik. So this is from the general expression we have for the f, f0. So we want to take the limit of this after k goes to 0. So this is then equal to 4 pi. If we use this expression here, so we write it in terms of the scattering length A. So this becomes A squared. For k goes to 0. That is the low energy limit. So we can compare this with what we get before for the Hart sphere scattering. Here we call that it is equal to 4 pi times the radius of the Hart sphere. So if we compare that, we can kind of understand why this is called scattering length. Just a definition. Yes. So those are two examples. And two relatively simple examples. So the key point is just to calculate the logarithmic derivative at the boundary from the inside solution, and then match it to the logarithmic derivative from the outside solution. That gives us the phase shifts. So it is actually quite simple. I mean, the concept is quite simple. Okay, in the remaining time, I think I would like to discuss a bit about the possibility of having a bound state. Maybe before I do that, I should also illustrate. Let me take that out first. I should describe this. I think this is more important. So I want to look at the solution of this scattering problem from a finite barrier. So actually this you can also see in figure 611 in the book. So this is UR here. So that's R times the radial solution. And let's say that we have some solution without the scattering potential. Like this. So this is no potential. And then we look at the case when we have scattering potential. So there are two cases. One case is when the potential is negative, so we use R. So we have an attractive potential. So we can draw the solution out. The potential looks like that. So now if we have the negative potential, then we expect that the particle will try to accumulate itself in the potential because it's negative. Yes. So this means that there will be a kind of contraction of the wave function. So you will kind of drawn towards the potential. So, and this shift here is given by delta 0 divided by k. So you see that the solution is shifted by delta 0 divided by k. And similarly, if we consider positive potential instead of negative, and we have the solution like this without scattering potential. And with scattering potential, we expect that the wave function will be pushed away from the scattering region. It's because this is a repulsive potential. So we expect the solution to be like this, something like that. So it's shifted away. So this shift here is also down to 0 point. Okay. So that's what happens in solutions. And this is also true for the higher L components. Except that the solution is, of course, different. It's more complicated. Okay, so I have still time to talk a little bit about this bound state solution. Bound states. So if we make the potential deeper and deeper, so if we have a negative potential, make it deeper and deeper, eventually we expect that there will be a bound state form. Particle will get trapped in the potential. So we will have a bound state. So when we have a bound state, then we have these radial Schrödinger equations. So you just write it schematically. Then we will have this kappa, and k is equal to I kappa here. Kappa like that. So the asymptotic solution, that is to say for large R, asymptotic, is given by exponential that decays. It's an exponential decay, yes. Instead of oscillating like you have in the case of free particle. When the particle is not bound, the solution is oscillating. But when we have a bound state, then the solution decays because it's bound. So actually there are two solutions. We also have the plus here, but this is not allowed, yes, because it diverges at infinity. So that's kind of the analog, the irregular solutions formed in a small r, because it diverges. So if we look at the general solution, we have this scattering amplitude, which we call S, and we have the outgoing solution, and we have the incoming solution, incoming wave, like that. So I don't worry about the constant because it's not important. It's just a constant. So that's another thing about scattering theory. That is the important thing is the ratio between these two things, not the constant. The constant is just not important. We can always fix that. So U0 is, remember, is a multiple R times the solution A0. Yes. So that's why I don't have this 1 upon R here. So I can write this as, okay, all like that divided by S0, okay. So that's a general solution. So now, if we have a bound state, then we have to replace the K with I kappa. So then this becomes bound state. We replace K with I kappa. So then the solution becomes 0 I kappa here, and then I have minus kappa R plus e to the S0 I kappa, like this. So this is just a constant, and it should be like this. So we see that this solution here diverges for large R, so it's not allowed. So not allowed. So this implies that the S0, okay, must diverge. Yes. So it disappears. We divide this by infinite number, so it disappears. So this is a kind of condition for having a bound state, that the S0 along the imaginary axis will have a pole. So poles in S0 along imaginary axis indicate formation of bound states. Okay, so this is kind of a qualitative discussion about bound states. Yes, I think we have more time. The rest is not so important, I think, for our purpose. So this is basically what we have for scattering theory. So are there questions? No. You can always ask later if you have questions. Just send me email. Yeah, so I guess next week, when is it? Is it on the 3rd of June? Let me check. Yes, on the 3rd of June we have this week exam. So that Thursday next week. It's very short, isn't it? Sunday week, a little bit over a week. Well, I hope you have enough time to prepare for the exams. And I will upload some examples from the previous exams. Okay, and tomorrow I think is the last exercise. Yes, tomorrow. Okay, so if there are no questions, then we say goodbye and then thank you.
Thanks.
Thank you.
Bye-bye.
Bye bye.
Bye. Thanks.